Sérgio Fenley and Thomas Barthelmé. Today is Thomas is going to talk us about collapse Anosov flow. Thank you.
Thank you. So yes, last lecture. Bit too loud for out there? No. We went from easy to hard. Now it's the end of the week almost, so we're going back to easy. Okay, so the goal is to explain for maybe the 2 or 3 of you that may not have understood everything about the example that Sergio presented at the beginning. Go a little bit deeper into the examples using this criterion that the BGHP criterion stands for Bonatti, Gogolev, Hammer-Linden, and Potry. So I'd like to, well, state that criterion because it's a very nice criterion to build partially hyperbolic. Then I will say a few words about, again, why those examples used using this method are so least space collapse Anosov flows. And then, if we have time, I'd like to talk about one of the natural questions that comes in with this definition of collapse Anosov flow is, so far, there's been those examples that just happens to be partially hyperbolic, and we prove that they are collapse Anosov flows. So they come, so from those examples, we get some self-orbit equivalence of an Anosov flow. And a natural question that we've been asking since we came up with that is, what classes, which self-orbit equivalence of an Anosov flow can be realized as one of those collapsed Anosov flows? And that was the last point of, if you remember the speech I made at the beginning, one of the goals of this mini course was to say, hey, look, those collapsed Anosov flows are a way to try to spot the missing examples. So the missing examples are exactly those beta that are self-orbit equivalents of an Anosov flow and that have not yet been realized as a collapsed Anosov flow. And so if we have time, we recently found out an example with Federico Salmoraghi of one of those missing collapsed Anosov flows. And so it has this nice property. We were wondering for a long time whether those existed, that it's isotopic to identity. However, it's not associated to a trivial self-orbit equivalence. Okay, so that's the plan for the lecture, and I don't know how much I'll go through the plan, but at least I really want to tell you about the BGHP criterion. So let's start with that. I was kind of debated starting with the definition, but I figured we gave you a lot of definitions already, so I'm going to start with a proposition instead, and I'll hide the definition inside. So here's a proposition of the BGHP. So suppose you have an Anosov flow, smooth Anosov flow, that phi t be an Anosov flow. So now a nice smooth surface. And let psi be a diffeomorphism, be a diffeomorphism, C1 at least, such that it preserves some kind of transversality of the bundles of the Anosov flows. So remember, we have an Anosov flow, so we have a bundle ES plus R times d phi dt plus EU. And so what you want is that psi is such that if you do deep psi of EU, it has to be transverse. It's transverse to ES plus this R d phi dt. So the image by psi of the unstable is still transverse to the weak stable. And the image by psi inverse of the stable is transverse to the weak unstable. Okay, so suppose you are giving that, then you can take your psi, hit it before by a large time of the Anosov flow, hit it after by a large time of an Anosov flow, and for t large enough, this thing that I'm going to call f sub t is a partially hyperbolic. Okay, so that was a very nice criterion that they come up with, and it's not difficult. It's a cone criterion. So how do we prove that? Well, take a cone centered near EU, and you can choose it small enough so that the image by deep psi of that cone is transverse to ES plus RX, right? It's transverse to the weak state. So let me write that. Let's do the proof. Take C cone, so unstable cone, such that deep psi of C is transverse to ES plus R phi dt. Okay, this I can do because of the transversality. And then, well, what happened to that cone? Well, I hit it first with phi t, so it gets even thinner. Then I apply deep psi, so it stays transverse to ES. And then I apply a long time of phi t, and hallelujah, I got back to some nice cone inside starting. Okay. So I won. Well, I won halfway. I need to do that with the stable cones also, but you do that with the inverse, and that's why we took this nice symmetric way of writing the diffeom. And so you get ft is partially hyperbolic for every large enough. Okay, is that okay? You agree that it's simple, right? So as promised, it's a beautiful criterion. The hard stuff, obviously, is to find some diffeomorphism that satisfy that. Okay, so the whole trick is going to be to try to come up with a diffeomorphism that verifies that. So maybe I should say some words. I'm going to call. I never liked the definition that the terminology that BGHP put. So I'm going to say that phi and psi are BGHP transverse. This means that phi, psi are BGHP transverse. And so the thing is, if you can find a couple phi, another flow, and psi, a diffeomorphism, such that they are BGHP transverse, then you win. You get a new partial hyperbolic. So you win, except that there's one thing that you need to prove. So the if you find, so once you find phi t psi BGHP transverse, then you get a partial hyperbolic. F sub t. Okay. The one thing you need to show also is that, well, you didn't end up being basically what you started with, right? You don't want this new fancy FT to be just the same as your original Anosov flow, because otherwise there would be a lot of work for nothing. So you need to find plus need to justify that FT is not the same. And by the same, you know, leaf conjugate or whatever you want, or in our definition, discretize Anosov flow, it's not the same as the time one map of phi. Okay. So before going, so that's the BGAP criteria. Beautiful thing. You just have to verify the transversality. Here, I'm going to say a word of how they justify that in the BGHP papers or in the series of BGP and BGHP. How do they justify that? They say, okay, well, if you make sure that this psi is not isotopic to identity, then this FT is not isotopic to identity, and hence you cannot possibly be the same thing as phi1, because you're not, one is not isotopic to identity and the other is. And so that's kind of it's a nice way of getting a difference, but it's a coarse way of getting a difference. And one of the nice thing of seeing them as collapse Anosov flow is we'll have a finer way of telling you whether an example built as an F sub T, as a BGHP example, is actually a discretized Anosov flow or not. Okay. So that's going to be one of the advantage. And that's why we managed to do that example, because the idea of the example is exactly the same as what is in BGHP. There's already the idea of this example in BGHP. In fact, in the previous paper with Hammer-Linden. However, they couldn't show yet that this was a new example because it's isotopic to identity. Okay. So now the second thing that I want to justify is, okay, give some ideas of why those BGHP examples are collapse Anosov flows. Okay, so here's a theorem. So this one is Sérgio and Rafael is, so any BGHP example is a least space collapse Anosov. So I'd like to, so it's one of the strong flavor of a collapse Anosov. Okay. So I'd like to justify that a little bit. So how do we do it? Oh, maybe before. So what I call the BGHP example is anything built using that example, that criteria. Okay, so what we have to do, so what we need to do, if I want to prove that something is a least space collapse Anosov flow, so goal is build a map big H from the orbit space of phi. Remember that was the orbit space of phi, which is, again, it's, you take m tilde and you quotient out by being on the same orbit, to what we called LC. So this is the center leaf space of F sub T, and this is a bit more of a difficult thing to build, but it's you know, we have those branching foliations. I'm assuming that things verify this orientability condition, so that I don't have to worry about existence of stable and unstable. So branching foliations, I mean. So you take the center stable branching foliation, the center unstable, you intersect them, that gives you a center branching foliation, and you can build a space this way. Okay. So our goal is to map any orbit of my flow in the universal cover to a center leaf of that. Okay. And I need to do what? Well, I need to show that this is a homeomorphism that preserves the invariance. So build a map and show that it is pi1 equivariant and a homeomorphism. And if I have that, I have this least space parameters. Okay. So what we have from the step, I mean, there's basically two steps. The first step is shadowing. Step one. I still have the proof upstairs of my BGHP criterion. So you see, when we did that proof, we took any small cone and then we hit it by those by this large time of IT, and we get an invariant cone, right? So it tells me that the unstable direction of FT is going to be as close as I want to the unstable direction of the original Anosov proof. Okay? Just by the proof, if I take T big enough. And same thing, if I take T big enough, I have the stable direction that is as close as I want. And I also have the center direction that is as close as I want. So by taking T very, very large, we have that EC for the F sub T, ES for F sub T, and EU for F sub T are as close as I want to to R d phi dt ES of phi and EU of phi. So that comes essentially for free from their criterion again. And then, well, you use the Anosov shadowing theorem. That's going to be telling you that, therefore, so by Anosov shadowing theorem, you can show that any any center curve, yeah, I can show that any center curve, center leaf of FT is epsilon close to a an orbit of phi, and that any orbit of phi is also epsilon close for the correct choice of epsilon, and any center, any orbit is epsilon close. So here it's in the Hausdorff metric sense. Is epsilon close to a center leaf, so unique. For any center leaf, there is a unique orbit that is that the direction. Yeah. There is a yes, two unique. I'm being a little sloppy here, but just want to give you the idea. So a unique orbit of phi, and any orbit is epsilon close to a center. And this epsilon goes to 0 as t goes to infinity. In our choice of the BGHP example, if you take t bigger and bigger, we can find this epsilon to be smaller and smaller. So that's a consequence of the shadowing lemma, and or more general version of the shadowing lemma. And now I want to build that map. So I want to build that map here. from the orbit space of phi to the center leaf space. Sorry? Oh, yes, yeah, those leaves are branching a priori, right? I mean, we don't know anything, but a priori they're branching. And in examples, you can show that in a lot of cases, they are going to be branching. So that's a step 2. We have to build H. So there's no, so from a center leaf, you can go to an orbit. And from an orbit, you know that there is a center leaf that is close. Right, there's a center leaf of FT and the orbit. Right, yeah. So you can have branching leaves that okay. Yeah. So okay, so now step 2 is building H. And well, this is, well, how do we do that? Well, we start with a center leaf, right? This step tells us that if I have a center leaf, there's a unique way to send it to an orbit. Okay, so that's how I'm going to do. So building H, or I get a map H. So sorry, I get a map H inverse from LC to the orbit space of phi just by this point 1. Right? From a center leaf, I have a unique orbit. Good. And I know it's surjective by 2. So by 1. So existence is by 1 and surjective by 2. And the fact that it's going to be a pi1 equivalent is because we build it in the universal cover. So somehow the pi1 equivalence is not going to be too much of a problem. Yeah. Yeah, so yeah, you have to go from here. It's you can really make it a center leaf and not just a center curve. But yeah, that's one of those annoying things that has to be done, but it works out. So it works out because you can. So maybe in one word, the justification is again you can approximate all those branching foliations by true foliations with a good control. Okay, so the left to show is injectivity. And once you have that, the continuity and the pi1 equivalence is not a big deal. The injectivity is kind of a pain. So maybe one word about, I mean, I don't know, or 3 hours as you want. So let's try with one word first of how we want to try to prove injectivity. So what would be the problem is, so the problem would be that H minus inverse of C1 and H minus inverse H inverse of C2 are the same, right? For two same center leaf, I'm sent to the same orbit. And I want to show that this cannot happen. So basically what we're going to do is, if you had something like that, so So if that happens, if this happen for C1 different from C2, then since you can make it close, you can actually get that it happens for two center curves on the same, say, weak stable or center stable. Then you can assume this also happens. This happens on same center stable leaf. And then you have, so what you have is that you're going to have a curve C1 on my center stable and a curve C2. They are sent to the same, so they are sent to the same orbits. It means that they're close, right? Because of my Anosov shadowing lemma. My map that sends center leaves to orbits is not that big. So if I have two elements that send to the same thing, they have to be close. They have to be like 2 epsilon close, something like that. Okay. And then you show that, well, in the middle, you're going to have, because you're going to have an interval of center. And then you're going to have I said center stable. Okay, so you're going to have a strong stable leaf that intersect that. And then now I'm going to read. So then you act by your partially hyperbolic. This center leaf becomes so act by f tilde to the, oh, it's stable, so to the minus n. I get this image of C1. So f tilde t minus n of C1. I have very far away that f tilde minus n t of C2. I know that those two things are far away. So they are so far away that they shouldn't be able to be sent to the same center, to the same orbit, because essentially because of expansiveness. But in between, I have this foliation by center leaves, this continuous foliation by center leaves. And I show that for, we show that for small enough center leaves, if they're close enough, they need to be sent to the same stuff. And then another close one needs to be sent to the same orbit. And then they need to be sent to the same orbit and sent to the same orbit. And then you realize that the bottom one and the top one have to be sent to the same orbit. So basically what makes the proof works in the end is the expansivity of the partially hyperbolic. Okay, and that's a very short way of, I mean, an unprecise way of proving that this map actually is. Okay? The core of the work is to find that you have those this interval of center leaves on a weak stable, and then showing that close by you need to be sent to the same. Or if you stay close, if you have two center leaves that stay close, their image under that shadowing lemma have to stay close also. Have to be the same orbit. Okay. So that's the argument. And that tells us that we have this map. And so that tells us that our, yes. Yeah, because so, well, yeah. So you're gonna get a contradiction by saying, so if I have center leaves that are very close together, they need to be sent to orbits that are, delta 2 epsilon close. Always. But there's never an orbit that is 2 epsilon close, because the flow, the Anosov flow is expensive. So if I have 2 orbits that are epsilon close forever, they need to be the same orbit. So I started with 2 close things that are sent to the same orbit. And then you keep on doing that, right? Since you have an interval worth of the center, you have like a 2 very close ones have to be sent to the same stuff. But then this one has to also be sent to the same stuff as one later. And so you break it up by, little pieces delta for uniform delta, and you have finitely many delta, but then this one has to be sent to that one. However, again, by the shadowing lemma, the orbit associated to this one is far from the orbit associated to that one. Okay, does that make more sense? And once you have done that inside the weak stable or a weekend stable, you realize that since they're, my C1 and C2 are close, okay, so they're inside a box, a foliated box. So if they were sent to the same thing, you can make a center on the same. So we got that theorem, and we're happy because we have we know now that all the examples built via BGHP are actually the strong version of collapse Anosov flow. And we're even happier because the way we build this map tells us that, the center leaves for F are sent to orbits not that far away. So we really have a good control on between how, the center leaves of the partially hyperbolic corresponds to the orbits of the Anosov flow. And this control is what can allow you to control what this beta is. So let me write this question again a little better. Okay. So now, this is what I just did. Well, anyway, this drawing is useless, so I can erase it. and I'll keep the shadowing because that's the one that is actually useful. So the conclusion is if FT is a BGHP example, so FT again, that does my phi t, my flow, composed with psi, composed with phi t. If FT is a BGHP example, then there exists a beta self-orbit equivalence of phi t such that well, I want to rewrite it in terms of my LSCAF. Remember? So for LSCAF, for this leaf space collapse Anosov flow, I had this map from the orbit space to the center leaf space. So and Sérgio explained how you could get the beta from the leaf space collapse Anosov flow, and I'm going to explain it again. So I had this from the orbit space to the center leaf space, and how from this do we get the self-orbit equivalence? Well, remember we had F tilde T, a lift of Ft to the universal cover. And so F tilde moves the center curves in center leaf space. And what I can do is I can do H to go from the orbit space to the center leaf space. Then I act by T tilde. Then I take H inverse. And that's a homeomorphism of the orbit space of phi, which is a self-orbit equivalence definition of self-orbit. So beta is equal to this. Well, beta tilde. Okay. And since I build that H using this shadowing lemma, what I know is that, well, basically beta tilde, when you see it as a map on the universal cover, so seen as maps on M tilde, the universal cover, beta tilde and FT tilde are not that far away from each other. So, I mean, they can be far on along the orbits, but they don't move orbits very far. So, seen as maps on M tilde, action of beta tilde on the center leaves is close to action. Action of beta on orbits of phi t tilde is close to action of F tilde on center leaves. So not only did we have this fact that those example B with the BJHP criterion are nice, they're collapse Anosov flow. They're collapse Anosov flows, and on top of that, we have a good control over this beta tilde must be. Because if you understand what happens to center curves for FT tilde, then you understand what beta tilde is. And remember, I think I still had it somewhere here. Yeah. There were two steps in building new examples. One is to find this couple that are BGHP transverse, and the other is to say that, you know, after all that hard work, you didn't end up at the beginning. So our theorem didn't help you with finding those BGHP transverse couples. However, you can finish, it gives you a finer way of finishing that. So now let's go back to the BGHP examples, and I'm going to give you an actual proper construction of these couples phi t and psi BGHP transverse. Okay. Questions before I get there? Yeah, so yeah. Sure, yes. Mm-hmm. As an action on, yes, because because center leaves are sent to close by orbits and vice versa. So globally, I don't move too much. Okay. Yeah. Yeah. See, very big. Oh, so that's another thing that I threw under the rug, but it's actually easy. So the BGHP criterion tells you that after some times you're partially hyperbolic and you stay partially hyperbolic forever. Our theorem tells you that after a very, very, very long time, you're least space collapse Anosov flow. So what happens between that very, very long time and the original stuff? Well, you remember the lectures of Sérgio, and he told you that least space collapse Anosov flows are open and closed. Well, then the original one is also least space collapse Anosov flow. But yeah, thank you. Okay, so there's this little trick. You have to go further for our theorem to work. However, in the end, it's not a big deal because you have open and close condition. Is that good? Yeah, see, open and close is useful. Who would have guessed, right? Okay, so now let's do some drawings. Yeah. Well, that's the thing. If you understand how, so somehow we can understand fairly well what the self-orbit equivalence of an Anosov law are. So if you know what happens to F, well, you know that this beta cannot be too far from F. So in particular, if you know that for some reason that, well, hopefully if I get to the example, we'll see. If you can see that in the universal cover, your F must move orbits far away, then you're done. Your SOE cannot be trivial. Okay. And that's the new thing that we get that just BGHP couldn't get because they didn't have as fine of a control. Okay. All good? Ready for drawings? Okay. Let's draw then. Oh, I'm gonna try to erase a board that I just didn't write. Or change. What was the oldest? I guess here. Okay. So examples. So remember what the drawing Sérgio did was. I'll give it to you again. Start with a surface, hyperbolic surface with a very long neck. Okay, and we want to show, and you look at geodesic alpha on your neck, and you want to show that D. So you take the then twist along alpha, so that let's say little d alpha is then twist on this surface S, on S along alpha, and the goal is we want to show that the derivative of this then twist with the geodesic flow is BGHP transverse. Okay, so that's my goal. That's one of the tricks that originally Bonatti, Gogolef, and Pottery used, and then it's nicer to see it with the BGHP criteria. Okay, so let's look at what this looks like in T1S. Okay, I'm gonna draw. So what is above alpha? I have a torus. Agree? I'll take the fiber above alpha, so I have a torus, and I'm gonna try to draw my torus like this. So far, it's missing some pieces. And I have the orbit alpha somewhere, and its opposites. This should be alpha. Okay, that's a piece of my torus, and I can look at the whole, tubular neighborhood of this alpha upstairs, and what this looks like is a very long tubular neighborhood. Okay. Okay, so in this drawing, the top is identified to the bottom, and the left is identified to the bottom. The back is identified to the right. Okay, and what happens to the flow? Well, here, because it's such a long and thin neck, what happens is you have the you have those transverse. You have this transverse direction where here the all the orbits that cross here, they're going to end up exiting, right? And then you have the stable manifolds of the alpha and the stable manifold of the alpha. Okay, because of again, remember it's hyperbolic geometry, so essentially either you enter. How do you not exist? Well, you can accumulate onto alpha, or otherwise you're going to have to go through. Okay. Good. So what is a den twist? What is the derivative of den twist? It's something where instead of going through straight, all my curves that go straight, I'll try to do a. So instead of having, say, something that goes straight along the bottom, I'm gonna make it so that it goes, once around in this direction, in the forward direction. So let me, the image should be something like okay. So this curve, this purple curve, is equal to d of the alpha of the orange curve. And same everywhere. Right? It's a den twist. So it's a den twist in 3 dimensions. So I don't do anything outside of that side of this tubular neighborhood of the torus. And then slowly I start pushing everything so that it rotates one full circle in the direction of alpha. Okay. And well, you see that I didn't move much, right? My orange curve is not that far in terms of its derivative from the purple one, because I took such a very long tubular neighborhood and it's skinny. So in terms of derivative, I didn't do much. Well, that means that I satisfied this PGHP criterion. My den twist moved the vectors just slightly, in some sense. I mean, the vectors, not the points. The points are moved, but the vectors are not moved. Okay, and okay. And so what happens is that since you verify this BGHP criterion, you build this example, and you get a partially hyperbolic. With our result, you get a least space collapse Anosov flow. And so one word is, instead of doing, so this work on a more general, just one thing for those who know already, and otherwise it's fine. You can do the same thing, and they did on Handel-Suston manifolds. So manifolds obtained by Handel-Suston surgery. And you realize that if instead of doing a twist where I twisted in this direction, I do a transformation where I move everything up along the vertical orbits. Well, I can do that in a Handel-Suston surgery, and what I get is those examples that I said I would talk about, and I don't have time to talk about, so I'm going to stop here. Thanks a lot.
Questions or comments? No more questions, no more comments. Well, if not, I guess that it's time to thank Sergio and Thomas for the very nice course. Thank you. Now we have a break of 20 minutes.